Hello everyone. Today we're going to be going through the nervous system. The nervous system is that allows our body to move. It's a arrangement of sensory motor and other neurons that divide it into the central and peripheral nervous systems. This is basically how our body communicates with all other parts of the body. It starts with the central nervous system. The central nervous system is made up, as you can see here, of the brain and the spinal. At the top of this, in the brain, is a very high-level functioning part of the body. It's divided into a number of different lobes and regions. It controls everything that we do. It is literally our nerve center. Hearing, speech, touch, pressure, every action that you control, or even actions that are out of your control, are handled by the brain. If there's any damage to the brain at all, it can absolutely affect other parts of the body. If you've ever had a concussion or any sort of hit to your head that had any sort of impact on you, you know that sometimes your speech or your smell, your hearing, or even your vision, how well you see, can really be impaired. So the regions of the brain are really important for our body to go. Below that, in the central nervous system, is the spinal cord, and you can see it's a very intricate mesh of pathways that deliver messages from the brain down to the body and from the body up to the brain. At the center of it is the spinal cord, and off of that are the nerve roots. Okay, those little projections you see coming off of each side of the. That spinal cord is protected by the spine, okay, the vertebral bodies, and we looked at those in class previously. You can see the big body of the vertebrae helps protect the front of the spinal cord, and then you can see the back of it, the projection off the back, okay, the spinous processes protect the back of the spinal cord. And then coming out of the two sections of it are those nerve roots. It's noted here on the picture as the dorsal root ganglion. All right, and those are really what delivers messages to the rest of the body. So messages come from the periphery to the spinal cord up to the brain, and as you can see, those messages get sent up to like the motor areas or non-motor areas, and the brain determines what message it needs to send back to make the body function. If it's a motor area and you're looking to lift something, it's going to cause your bicep to contract to lift that part of the body. If it's a non-motor area, if it's for the heart to beat or your lungs to inhale, it'll send messages there. So as you can see, the brain comes down. That's the central part you see there, the brain and spinal cord. That's noted here in the kind of rose-colored structure. Then the blue structures are everything outside of it. And if you remember when we talked about the different regions of the skeleton, the brain and spinal cord are part of the axial skeleton, and the peripheral nerves are part of the appendicular skeleton. So when we look at the peripheral nervous system, those peripheral nerves are made of ganglion. Remember, we saw the root ganglion coming out of the spinal cord. So the ganglia, the neurons, and axons. All right, so what do those look like? Let's dive into that. So you can see it comes out of the brain, spinal cord, and then those nerves can be big bundles that you see coming off the shoulder, okay, or they can be real thin, tiny nerves. So it depends on what region of the body we're speaking about. But when we look at different regions of the body, we have to look at the different regions of the spinal cord and of the spinal column. If you look at the top of the picture, you have the cervical parts of the spine, and then you have the thoracic, and then the lumbar and sacral. So if you look at the cervical area, there's 7 vertebrae there, there's 12 at the thoracic, there's 5 at the lumbar, and 5 at the sacral. Easy way to remember that for me is if you have breakfast at 7 a.m., there's 7 cervical. You have lunch at 12 noon, there's 12 thoracic. You have dinner at 5. That's the lumbar. There's 5 p.m. So those are all the movable segments. And then below that, below the lumbar is the sacral, that kind of tailbone area you see there. And those are fused vertebral facets. So, there's 4 basic regions of the spinal column, okay? But if you can see over on the right now, that image, you have the spinal nerves. The spinal nerves, the numbers are off just by a little bit. They match up in the sacral, lumbar, and thoracic areas, 5, 5, and 12. But there's one extra spinal nerve in the cervical area, and that's because there is a nerve that comes out just above the first vertebrae. All right, just want to let you know, give you a little heads up here. We are going to see a dissection in the next image. So if this is not suitable for you, you can quickly fast forward by about 30 seconds. What's important to see though, okay, with this image is that you have an intricate web of tissue. If you look down the center is the spinal cord. Coming off of those, you see those ganglia, those dorsal ganglia that I said that kind of shoots those messages out to the rest of the body. The red, you see red little vessels in there. You see blue kind of veins. You see some fatty tissue, you see muscle. So it's really an intricate web of tissue there. Okay, moving on. All right. So in the peripheral nervous system, as I said, you have nerves and ganglia that are outside the brain that send messages to the rest of the body. Okay. This is that connection between the central and peripheral, all right, that sends stuff to the limbs and the organs, okay? You have sensory nerves, okay? We call those the afferent nervous system, or afferent nerves. That brings messages to the central nervous system. I like to say it brings it at, afferent, at, okay? Then you also have the motor nerves, which are the efferent nerve pathways. That brings information from the central nervous system. So I say it efferent, it exits the brain. So those motor nerves exit the brain and sends those messages to the rest of the body. Both of these divisions, both of these branches allow the central nervous system to either have that voluntary control. Again, you go pick up a glass, pick up a pencil, or involuntary control of your body, which is like your organs, your nerves, things, your hormones, digestive systems. That's just happening, right? You don't think about those things happening, but they are happening. And those are some of the involuntary systems. So within the peripheral nervous system, you have 2 major divisions of the motor side. Okay, this is the motor side. This is what causes us to move. You have the somatic nervous system, which is skeletal, somatic, skeletal, okay? And then you have the autonomic nervous system, which are all those things that are happening automatically. So those are your glands, okay, that secrete enzymes and hormones. You have your heart, you have smooth muscle and digestive tract that helps the body go. And those are automatically happening, right? So we don't think about those things as you're sitting there. You're not thinking about what you had to eat earlier today and I need to digest that. It's just kind of happening. Whereas the somatic system is the skeletal muscles that you have to think about. All right, so the somatic is our voluntary control. All right, what are we responsible for? Well, we're responsible for coordinating the movements of our body, okay? Those systems receive external stimuli and cause the body to move and act in certain ways, all right? And it takes care of, or what we call regulates, activities that we are consciously aware of. The autonomic nervous system is involuntary. It's just happening all the time. Within that, there are 2 divisions, okay, 2 branches. You have the sympathetic and the parasympathetic nervous system. So the sympathetic system is that kind of sympathetic kind of stress response. It's that fight or flight response of your body. So if you think about a situation when you were really nervous or scared, what sort of symptoms or signs that you were nervous did your body give you? Think about those for a minute. I'll wait. Okay, we're back. So did you think about when you were nervous before or scared, maybe before a big test or a big battle that you were going to have, a big game or something like that? That was something that maybe you started to sweat a little bit. Your heart rate was raising, and you got kind of anxious. Maybe your stomach didn't feel quite right. So if that happened, then your parasympathetic system hopefully would kick in. Okay, this actually helps you to be relaxed and under control. You take some deep breaths, you use some mental imagery, you use some things that are going to kind of calm your body down. So these systems work opposite and help your system to really kind of stay in balance or homeostasis. So you can see these two big divisions, how they kind of split off. The central nervous system is pretty straightforward. You have the brain and spinal cord. Not that it's any less important. Actually, it's more important, but it's very focused on what it needs to do, and there's not all these extraneous distractions or parts to it. Whereas you can see the peripheral nervous system is a lot more subdivided and has a lot more small. All right, so within the body you have nerves. Nerves are very specialized, okay? If you have nerves in your feet, they're specialized to just your feet. You have nerves in your hands, they're specialized to just your hands. So they're nowhere else in the body. The important thing to remember is nerves work off of electrochemical signals that go to and from the brain, okay, and spinal cord. So we're going to get into what that looks like here. So as you can see here, if you take the top of this graphic, these are the sensory nerves. Okay, these are the afferent receptors. That is something where they're receiving external stimuli. Okay, and they're sending that information, if it's hot, cold, sharp, dull, they're sending that information to the spinal cord, okay, to the central nervous system from the periphery. That information gets sent up to the brain processes it. The brain is then going to send a message back through the somatic motor neurons, okay? It's going to go through the efferent nerve pathways, all right? It's going to send those messages all the way back down from the brain to the spinal cord, through the efferent system to the skeletal muscles, right? And sending that message of, hey, that was a very hot item that I touched. I need to put it down. So then those skeletal muscles, after receiving that message, those skeletal muscles will release and put that hot item down. Okay, so that's how the afferent and efferent pathways happen. They happen very fast. It took me, 30 plus seconds to explain it, but this happens very fast in our body and is under our voluntary control. But the autonomic nervous system is very quick and it's just happening all the time. So again, it's those cardiac muscles, it's those glands, there's hormones that have our body, the systems in our body, like the digestive system, just sort of happen. And they're automatically happening all the time, even right now as I speak and you. So how are nerves structured? They basically have the same parts. You have a cell body, which has the nucleus, okay, has the center. You have dendrites, which are those finger-like projections that actually grab signals from another neuron or another receptor and pass that signal along. It's kind of the messenger. It's grabbing those messages. And then the axon is a tail-like structure that goes from the cell body to the next neuron. Okay, so you're going to see what that looks like. So you see the cell body is a kind of reddish orange in the middle. The dendrites are those finger-like projections. The axon transmits that nerve signal, okay, that message, okay, along itself to get to the dendrite, okay, and then you can see the synapses, like that connection, okay, between the two points. All right, so you can see how that nerve kind of travels from one neuron to the next, and it can stretch for miles and All right, so when your brain receives a signal and it sends the information back out to the rest of the body, what does that look like? Well, that's called the efferent pathway. Like I said, it exits the brain. That's the alpha motor neuron. Okay, motor movement. All right, so alpha motor neuron. This is what's under our conscious control. All right, so again, this can be several feet long. Okay, from the spine to the foot, for example, is one neuron. So let's say the top of this picture, let's say that your finger touches something very sharp, right? That's that stimulus, that external stimuli that's giving you information, sending sensory information to the brain. Okay, it's got to go through the spinal cord, okay, through that sensory neuron to the spinal cord, okay. The information's got to get up to the brain. It's got to go back down to the spinal cord. That message was, hey, this is sharp. I need to remove my hand from this area. And that message comes back down the motor neuron. Goes into the effective nerve pathways, okay, and it pulls that hand away from the sharp object, as anybody should. All right, to transmit this signal, though, there's a thing called the neuromuscular junction. So it's a very small gap. You saw on that graphic a couple slides ago, there was a synapse, okay. The synapse is between the neurons, okay, where chemicals are released, okay, and it binds to membrane, so they don't actually touch. So we're going to see this neuromuscular junction, the NMJ. So you can see this right here, the neuromuscular junction right here doesn't actually touch, but it comes very close to the motor end plate, all right, and those chemicals, those neuromuscular chemicals will jump across, okay, and get into the motor end plate. And you can see down below on this graphic towards the bottom, you can see the actin and myosin. Remember those blue and red kind of binding particles that we looked at in the previous lesson? That's what actually helps the muscle contract. Okay, so this is our neuromuscular, nerve and muscle, neuromuscular. So at the end of it is the terminal branch. Okay, that is where several dozen, up to a couple thousand of these terminal branches may be. So a terminal branch innervates a single muscle cell. So a terminal branch at the end, okay, the end of the neuron, okay, innervates a single muscle cell. Now, they don't actually touch, okay, so there's a membrane. Think of a membrane like covering almost. It doesn't actually touch, contact the cell, okay. So I want you to think about this is one motor unit, okay? So one unit causing one muscle contraction. So you had these alpha motor neurons, and all the fibers that it innervates is a motor unit. Okay, that's the term for it, is a motor unit. So the motor unit is the only one comprised of a single type of muscle fiber and its neurons. So if you have fast twitch fibers, if you have slow twitch fibers, okay, it's those motor neurons that innervates those specific types of muscle fibers. They don't cross over, they're very specific. And the smaller the ratio of neuron or nerve to fiber, the more skilled our movement is. So if we think about how fine-tuned our body needs to be for our eye movement, okay, then we have a smaller ratio of neuron to fiber. That means I have one neuron and it's innervating 100 fibers versus a large ratio of, let's say, one neuron to 800 fibers. That's just like bending the knee. I don't need to be as skilled with that. That's what we call a big gross motor movement, motor skill. It's not fine-tuned. It's not surgery. It's just, hey, I'm getting up out of my chair. So you can see on this magnified image, you have the motor end plates innervating muscle fibers. Okay, these are those red strands you see. I think we may have seen those on the anatomage before. Those are single muscle fibers. So those are motor end plates. Those are nerves coming down. You see a little ball at the end. That's the terminal branch. So when we actually recruit motor units, okay, what does it look like? So we have certain high demand and low demand activities. Like low demand activities, lifting a pencil, lifting a remote control, lifting your phone. lifting a small glass of water. Those are all small, low demand actions. They don't require a lot of motor units, okay, a lot of basically muscular strength. So we don't have to really stimulate those muscles to fire, okay? We can, it's low response. But high demand activities like lifting a child, lifting a car, lifting a very heavy school bag, okay, those require a lot of muscular force. We have to recruit a lot, okay, of those motor units. And they all have to fire at the same time. It's the all or none principle. They all have to fire at the same time in order to make that movement happen. And they require a lot of stimulation. Okay, so there's got to be a lot of neurochemical action happening, a lot of nerve transmission at that point. A lot of those electrical impulses have to happen and stimulate that area. If you've ever had electric stimulation therapy for injury or something, the higher the intensity, the higher the stimulation, the better that muscle contracts. This is that same idea. And those high demand activities are going to cause more fatigue. That's just the way it is, right? Think when you really, really contract something, you really, if you do it very, very intensely, 5 times, like high, if you're going to squat and you load a lot of weight onto that bar, but you only squat it 2 or 3 times, your muscles can be very, very fatigued because it's a high demand, high motor unit recruitment. So because of that, smaller, slow twitch fibers are always recruited first, right? If you remember slow twitch, they are fatigue resistant. So they can go on for a long, long period of time. We don't have to call in the dogs. We don't have to call in the fast twitch fibers. We only bring those in maybe at the end. So slow twitch, we can continue to call because they have what's called a lower threshold for depolarization from sodium. Okay, if you remember those electrochemical the electrochemical principle I spoke about a few slides ago, muscle contraction takes place when neurochemical transmitters are released. Okay, sodium is a neurochemical transmitter. So lower threshold means it doesn't require a lot of stimulation, okay, for this to happen. Okay, but it takes high frequency, high stimulation, okay, to activate fast twitch fibers. So think about if you really cranked up that electrical stimulation unit, okay, to kind of shock yourself, if you will. It requires a lot of it for those fast twitch fibers to kick in. So when you're trying to lift something heavy or run fast. Okay. The sensory receptors are what gets the information and passes it up the channel, passes it to the spinal cord, passes it to the brain. Okay, that's a sensation. They are internal skin receptors associated with the neurons, okay, that send information to the central nervous system. So these sensory nerves are what detect heat, cold, taste, sharpness. Okay, we encounter these things day in and day out. But there's a small division of those called sensory receptors. They're called proprioceptors. Okay, so proprioceptors are very, very important for us to. So proprioceptors we use every day. Okay, they detect your body's motion or position. Okay, so if you stand up, okay, so get up out of your chair or whatever hopefully you're not driving, you listen to this. Get up, stand there and balance on one leg. Okay, right now your body is using all of your senses, okay, the subdivision of those proprioceptors to keep yourself balanced, okay. Now, carefully, all right, close your eyes and see how balanced you still are. It's probably a little bit harder to do because now we've taken away some of that external stimuli to keep you balanced. We've taken away your sight. Okay, so these proprioceptors that keep us balanced and keep things in alignment, they're in muscle belly, tendons, joints, and in your inner ear. So if you ever had an infection in your inner ear, and some people do, they can begin to feel dizzy. sometimes they refer to it as the sixth sense. They're our body's own internal GPS. It gives our body feedback day in and day out, and is important for everything that we do to maintain homeostasis or balance in our life. So there are some specific proprioceptor types. Okay, so first is called a muscle spindle, and if you've ever had a physical before, you know what this is. You can see from this picture. Okay, they're located throughout a muscle. These spindles actually take information that detect muscle length and stretch, all right, and send information. Okay, so for example, like the knee jerk reflex. If you see in this image, okay, you're sitting at the edge of the examination table. The medical professional hits the knee, okay, with a reflex hammer, hits the patellar tendon. That message, you can see from this graphic, the orange kind of pathway, the stress receptor, sends a signal up to the spinal cord. It doesn't need to go to the brain. Okay, it gets to the spinal cord. That spinal cord then sends a message back to the rest of the body, okay, through the motor neuron, or back to the leg, through the motor neurons, and that determines that there is a change in the length, okay, of the muscle, of the soft tissue, and so that it does not injure itself, it will contract those muscles and cause that leg to extend, cause the biceps femoris muscle or the quadriceps femoris muscles to extend to try to protect that area from being damaged, and you kind of kick the leg outward. All right, so that's a quick motion and a quick movement. Doesn't have, it's again a reflex, very fast. The information does not go all the way up to the brain. It gets to the spinal cord, and the information is sent back to the leg so it can quickly. This is another example of a reflex, okay? And you can see on this image, you're going to touch something hot, okay? That's the sensory nerves. That's the red line or nerve pathway that you see. The spinal cord determines what is happening. There's a response that's generated to say, hey, that's hot, okay? So the relay neuron sends the information from the sensory neurons to the motor, right? That's that link. If there, for some reason, is a disconnect of the relay neurons, that arm will not pull away and that person can continue to get burned. All right, so you have to make sure the sensory, motor, and relay neurons are all working in the body and are working rapidly. Second proprioceptor type is the Golgi tendon organ. This is located within tendons. It detects tension generated by a muscle. Okay, so if you think about a stretching, okay, if you go to stretch, if you go to lay down and pull your leg like you're stretching your hamstring, pull your leg back, flexing your hip, you can hold it there for 20 to 30 seconds. At some point, that tension, okay, will in that leg will say, hey, relax, or you're going to injure yourself more. Okay, so it shuts down that alpha motor. So you can see this image right here. Okay, the muscle tendon junction feels tension on that connection. So it sends that information to the spinal cord. The spinal cord says, hey, relax, okay, or we're going to cause more damage. So it actually causes a relaxation response, which works opposite of that tension response. So the body will relax that tissue and you'll be able to stretch it more or keep. So the important thing with all of these nerves is to remember that these messages are key. It's our body's messenger system that causes all of our actions, whether they're under our control or not under our control, to happen. Hope you enjoyed today's lesson on the nervous system.